Okay, in this video we're going to continue looking at some additional electrophilic and otherwise additions to the alkene group. The reaction that you see here at the top is called halogen addition. Okay, so in this reaction here we are taking a halogen molecule, usually chlorine or bromine, occasionally iodine, but not always. Iodine, the delta H for this process is so close to zero that a lot of times it just doesn't occur very easily. Fluorine, too many side reactions occur. Basically, it substitutes everywhere. So you don't typically see fluorine being used in this reaction. Okay, so in this reaction, we're adding one halogen to each of the original alkene carbons, and of course the what used to be a carbon-carbon double bond is now a carbon-carbon single bond. We've essentially replaced the pi bond of the alkene with two equivalent CX sigma bonds. An interesting fact about this reaction is when you look at a cyclic system, you can see that the reaction is clearly an anti-addition. It gives you only the trans product. Okay, notice how in this product here the X groups are on the opposite sides of the molecule. Okay, so this is a first case of something we've had called an anti-addition, where the two halves of the reagent add to the opposite face of the alkene. Okay, so let's look at the mechanism for this reaction, and first let's look at how we can regard halogens. Okay, the XX bond is what we call very polarizable. It can distort the electron cloud to match whatever is in the environment. So let's put an anion in the vicinity of bromine. What we would find here is that bromine would reorient the electron distribution in the bromine-bromine bond so that this bromine that's closer to the anion would get a partial positive charge, and this other bromine would become partial negative. Okay, so we can have an unsymmetrical electronic distribution to match environmental conditions. In an extreme view, we can treat bromine or chlorine as if it's this salt here, Br plus, Br minus. Okay? Although it's not an ionic compound, this way of looking at it works surprisingly very well, okay, for explaining a lot of the things that you see these reagents do. Okay, let's look at the mechanism and see how we can account for the anti-stereochemistry. All right, so let's just look at cyclohexene here. If we think of bromine as one of these being a plus and one of them being a minus, we can get a classic electrophilic addition to a double bond just like we've seen before. This would produce a carbocation adjacent to a bromine. Bromine has all of these lone pairs here, so any of these lone pairs could now react with the carbocation to make a bond. This was a three-membered ring, and this species here is called the bromonium ion. The bromonium ion has an octet for all of the electrons. There's no carbocation. Every atom has an octet. Okay. Most current thinking here is that we actually bypass this intermediate here. We don't really form it, that bromine adds directly to make the bromonium ion. However, there are cases where the alkene is polarized. We'll see some of those later, where it's thought that the reaction might occur in two steps. But for most of the alkenes that just have alkyl groups on them, this is really what's thought to be happening, the direct formation of the bromonium ion. All right, let's redraw it. We're going to draw it in this perspective here, where bromine is occupying the top face of the molecule. Okay, and what happens here is that in the second step, the bromide anion that you generated right here is now going to come in. And it's going to attack from the side that's opposite the bromine. And this is called a nucleophilic displacement. And this is the main theme of future studies in Chapter 8. There's no perfect way to teach organic chemistry. No matter how you order the chapters or whatever, you've always got to bring something out of the future to explain a present phenomenon. So just take our word for it for now that these types of reactions, the nucleophilic displacements, always occur from the backside of whatever the bond that's being broken is. So this, we're breaking the carbon-bromine bond here, and the new carbon-bromine bond forms on the opposite side of the one that got broken. All right, because of that, what we see here is that bromine and bromine are on opposite faces of the molecule. This bromine's on the top face, this bromine is on the bottom face of the molecule. So that is where our anti-addition comes from. Okay, if we do this reaction in the presence of water, oftentimes it's just water solvent, or it's just some other solvent that just happens to have a lot of water in it. Sometimes we just call it wet solvent. We see that we make this type of compound here, and this is known as a halohydrin. Okay, and X in this case can be chlorine, bromine, or iodine. It makes HX as a byproduct, so often when you see this reaction run, some people will add a weak base or something like that to sop up the excess acid, but we'll just present the reactions in this chapter this way. Okay, like the halogen addition, the halohydrin formation is also an anti-addition. Here we see that the OH group and the X group have both added to the opposite face of the molecule. We get the trans stereochemistry. We'll find that this reaction here is mechanistically quite related to the halogen addition that we saw in the previous slide. Okay, so let's look at this reaction in detail. You find that this one compound here, 1-methylcyclohexene, is the best substrate for illustrating the reactions in this chapter. It's what we call an unsymmetrical cyclic alkene, so you can see all of the regiochemistry and all of the stereochemistry issues when you use this molecule as your substrate. Okay, so what happens in this reaction? It starts out exactly like the previous one. We make the bromonium ion, shown here. So here's our bromonium ion. All right, we now have to consider the bromonium ion equilibrating with the carbocation forms. It's more likely to equilibrate with this form, right? Because this carbocation is tertiary, whereas this carbocation is secondary. Okay, if we think about all of these compounds being in equilibrium, we would arrive at a composite picture like this, where most of the positive charge would be at bromine because the bromonium ion is the most stable of all these, but there would be more positive charge here than here. So the nucleophile, which is water, is going to attack here. Okay, so this is how we get this regiochemistry, okay, where the water comes to the more substituted carbon, the bromine to the less substituted carbon. In the final step, we just pull off the extra hydrogen with bromine, and this regenerates our other product, HBr. Okay. All right, so I just want to say another thing about this. Depending on how far we move the bromine, we could go as far as to call these resonance structures. I'm not sure. It's kind of a debatable issue. I'm going to just call them equilibrium structures, but you sort of get the idea that the tertiary carbocation is more stable than the secondary carbocation, and that is why we get the oxygen here. This is referred to also as the Markovnikov product because water, or this is the nucleophile, and this is the electrophile. Okay, so this is consistent with a Markovnikov description. Okay, one other issue here is we made Br minus, but I'm using water as my nucleophile. Why isn't this reaction just behaving exactly like the other one and making the dihalide? Well, this is because water is actually a better nucleophile or a stronger base than bromide ion. When you think about it, HBr plus water goes to give H3O plus Br minus. That's the Bronsted-Lowry equation. Because that goes to the right, that tells us that water is actually the stronger base. And also, if we're using water as a solvent, there's a lot more water molecules than bromine molecules, so they're outnumbered. Okay, we'll revisit halohydrins, I think, in chapter 16. We'll find that they're very useful for making the type of compound known as an epoxide. All right, that's actually the next reaction. We're not going to make them from bromohydrins yet. We're going to make them a different way. All right, so if we take an alkene, and this type of compound is a peroxy acid, okay, the OO bond is a weak bond, so it wants to be transferred quite readily. Okay, so when you react an alkene with a peroxy acid, you generate an oxygen in a three-membered ring, known as an epoxide, and you generate as a side product the ordinary carboxylic acid, the one that only has two oxygens and has no OO bonds. Okay, what does a carboxylic acid look like? Remember that it's this structure right here. Okay? All right. This is also a syn addition. It's hard to see it as a syn addition here because the only thing we can use is have used so far is cyclic olefins to illustrate that. But let's use acyclic alkenes. All right, so if we take the transalkene, all right, hydrogens here, remember, are here also, and treat it with a peroxy acid, in this case peroxyacetic acid, we'll get the epoxide where the ethyl groups are in a trans relationship. And if we take the cis epoxide, we get the product where the ethyl groups and the hydrogens also are in a cis relationship. This is another way of looking at something as being a syn addition. Okay? All right, the mechanism, it's not really a mechanism. It all occurs in one step. There's no intermediates or anything. Basically, the alkene acts as a nucleophile attacking the epoxide, or attacking the outer oxygen of the peroxy acid, and we form a bond here. Okay, and the hydrogen transfers up here, and the double bond reforms over here. It's a concerted transfer of oxygen. It's not really a mechanism. The most important thing about this mechanism probably is the fact that the alkene is acting as a nucleophile and the epoxide is acting as an electrophile. All right, if we look at all of these reactions that we've seen before, except maybe hydrogenation and maybe hydroboration, we can regard these as reactions where electrophilic addition to an alkene is taking place. Alkyl groups, remember in chapter 4, we said that because they have the ability to stabilize carbocations, they're acting as electron donating groups. This means that they're going to enhance the Lewis basicity of the alkene group. We're making the alkene pi bond is becoming of higher basicity. Okay, so the alkene pi bond becomes more reactive as we add more alkene groups to it. All right, so let's take hypothetically this reaction here where we're taking 1 mole of monosubstituted, 1 mole of this, and 1 mole of any of the reagents. We'll just use HCl. Okay. BH3 would probably also be an exception as well. Okay, so if we did this reaction, we would find almost all of the product comes from adding the HCl to this alkene here, because this alkene is more substituted, it's more electron rich, therefore it's more Lewis basic, more nucleophilic, so it's more reactive to an electrophilic reagent. Same thing if we treat an epoxide, treat a dialkene. This is called a diene, which has 2 alkene groups, with a peroxy acid. We would find that you get mostly the compound from adding the epoxide to the more substituted alkene group. This product here would be the major product. The other product from adding to the other alkene would be the minor product. Okay, so let's look at a problem here. This is just a classic problem. You should do it yourself, then pause the video and then restart it. You need to draw the correct diastereomer here when you're predicting the products, if the alkene is cyclic or if we're making a ring as in the last one. Okay, we want to draw the correct stereoisomer, be it cis or trans. And another important issue is that the benzene ring and this thing here, the C double bond O, are not reactive to any of the reagents in the alkene chapter. All right, so this first reaction is going to occur right here. This is going to be an anti-addition. And the product we get should be this product right here. Bromine should be on opposite sides of the molecule. In this one, next one, we have 2 alkenes. One of them's disubstituted, one of them's trisubstituted, and the trisubstituted alkene is going to be more reactive to an electrophile like chlorine. Okay, so if we're very careful to add 1 mole, we expect a highly selective reaction resulting in this compound here. And remember that we're adding water to the more substituted carbon and chlorine to the less substituted carbon. Okay. And the last one, we're going to be adding the peroxy acid to an alkene. You have to look at the alkene and determine whether it's cis or trans, or E or Z. And this one is definitely trans, so the epoxide that we make should be the trans epoxide. It should have the hydrogens on opposite sides, and it should have the original alkyl groups on opposite sides as well. That's be it either the methyl group or the dichloroethyl group that you see there. Okay, so that's the predicted product there. All right, let's look at a couple of other reactions before I end this video. One is going to be the ozonolysis. Ozone, we introduced that in chapter 1 when we're looking at molecules that show resonance. So ozone was one of the simplest examples of a molecule that shows resonance features. Ozone is very reactive to an alkene. Okay, so if you want to think about how does this reaction go, not in the order that I put the arrows, but that's one way to look at it. Okay, so ozone adds to the alkene group to make this compound here initially, which is molozonide. It's not a very stable compound. At very low temperatures, a molozonide rearranges to an ozonide. Okay? An ozonide would just sit there waiting for you to isolate it. It's a little bit explosive. Its instability stems from the fact that it has an OO bond. Okay? But if you treat an ozonide without isolating it with reducing agents, we're going to use in most of our equations, or actually in all of the equations that I present, we're just going to use zinc metal and aqueous acid. Some alternatives to that include a compound called triphenylphosphine and a compound called dimethyl sulfide. Those could also be used as substitute reducing agents. Okay, the product that you get from this is actually you get two products from your original alkene, okay? And we call this functional group an aldehyde if one of the R1s or R2s is a hydrogen, and we call it a ketone if neither of them are hydrogens. The net result here is that you've actually cleaved your original carbon-carbon double bond. Carbon-carbon double bond becomes two C double bond O systems. Okay, so let's look at a few examples of the ozonolysis reaction. The alkene here, we're going to cut it in half, and it's going to produce two fragments. The original carbon-carbon double bond here becomes one of these becomes a carbon-oxygen double bond, and the other side also becomes a carbon-oxygen double bond. So the molecule gets cut in half. All right, here's another example here. Again, we're going to cut the molecule right there where the carbon-carbon double bond is, and here you see we get the two fragments where the C double bond O exist where the C double bond C used to be. An interesting case occurs when you have an alkene within a ring. Alright, so if the alkene is within a ring like this, what you find here is that there's still a connection between the two carbons. Okay, so you're going to cleave this bond, but these two carbons are still connected through this framework over here. So the ozonolysis of this substrate here, fluorine's not going to be reactive, is going to produce one compound that has two C double bond O groups in it. Again, each of these carbons became a C double bond O, but because they were connected in the original structure elsewhere, they're still going to be connected in the product. All right, so here's a let's do one more reaction, then we'll do a problem here. This is the last reaction we're going to look at in this video. It's going to introduce the concept of polymer chemistry. Okay, so we've seen alkenes react with an electrophile. Another electrophile alkene can react with is a carbocation, and we'll see that when we see the mechanism for this reaction. So we take this compound here, 2-methylpropene. Now let's say 2 or more of these. And we treat it with neat sulfuric acid at various concentrations. What we'll find here is that we get a mixture of compounds. This is the simplest compound you can obtain, where two of these come together. Notice this has 4 carbons. this has 8 carbons. But we can incorporate multiple units of this starting material to make compounds of considerably higher molecular weight. Okay, sorry, this parentheses here is in the wrong place. It needs to be there. Sorry. Okay, so that's where our parentheses is. Let me redraw it here. Okay. All right. Depending on how many of these are incorporated here, we'll call it either a polymer, that's where we've incorporated a very large number of them, or we'll call it an oligomer. Geez, spell oligomer right, will you? Okay. Where it's a much smaller number. I'm not sure where the boundary between oligomer and polymer cuts off at, but anyway, we'll look at the mechanism here and see how these products are created. Okay. The structure that's inside the parentheses is what we call a repeating unit. And the repeating unit should have the same formula as our monomer. Okay. All right. So the repeating unit here is these 4 carbons. 1, 2, 3, 4. And should have 3, 6, 7, 8 hydrogens. 3, 6, 7, 8 hydrogens. Okay. All right. So when a compound is engaged in a reaction that's going to make a polymer, we refer to the starting material as the monomer. Okay? And we could refer to the simplest product here that I showed first as the dimer. Let's look at the mechanism for this process. It involves something we've seen before, protonation of the alkene group. Okay, so sulfuric acid is a strong acid. It's going to protonate the alkene. The 2 hydrogens that are already there are going to be joined by this other hydrogen to make a methyl group, CH3. This generates a tertiary carbocation, which can now react as an electrophile. It can be attacked by the nucleophilic alkene group, and this involves now making a compound that's dimeric. Okay, we say that it has 8 carbons from a starting material that had 4. Classic alkene formation, like we saw in the previous chapter, like this, is going to lead to this product right here. However, there's nothing to stop another molecule of this from coming in like so and adding together, and this process can keep happening over and over again, and ultimately you can incorporate lots and lots of these into the molecule. Okay, this is not the best way to make a polymer. We're going to look at polymer chemistry in the next slide and see a better way to do that. Okay, let's end this video with a couple of problems. Okay, so here you're supposed to just predict the product of each reaction, or in the second case you're actually going to predict the starting material. Again, pause the video, do the problems, and then look at the answers. All right, so here we're going to cut the molecule right there. We're going to leave the rest of these oxygen groups alone, focusing only on the double bond, so that will be one of our products. Sorry, I don't need to draw them because they're already going to be drawn in the slideshow. I hope I didn't draw them right where they're going to appear. Yeah, I drew them exactly where they're going to appear. Well, that sucks, so let me just draw that again. Okay, All right, there we go. All right, so there's the one product, and the other product is the one on the far right. Okay, in this next one, we're predicting the starting material, and it says to give an answer where there's no other compound produced. So it's an ozonolysis, so you know that in our starting material, these carbons had to be connected. All right, so the best answer you could give would be the simple one over on the left. If you wanted to be fancy and show off, you could design a more exotic molecule that, like the one on the right, but this would be the simplest correct answer. Let's see, why would this not be the correct answer? The reason it's not the correct answer is because the directions say that you're supposed to provide a starting material that will produce this and no other compound. This will also make another fragment. Okay, so this is a better answer right here. All right, so in this last one, we're going to do the reaction we did in the previous slide, except for a more exotic substrate. We're telling you to focus on the product that's a dimerization. Notice that the starting material has 7 carbons and the product has 14. Okay? All right, so, and it also has 12 hydrogens. And it's got 24 hydrogens. So we know that this is strictly a dimerization. Okay, so what's our final product? That should be our final product. How do we make it? Well, we're going to make it by protonating here. Okay, that's going to make our carbocation. We're going to bring in another one of these. Okay, this is going to add this makes the carbocation, and Zaitsev's rule say that we really should form the alkene over here in the 6-membered ring, because that's a tri-substituted alkene. Actually, both of them are tri-substituted alkenes. Alkenes are more stable inside rings than outside. I guess, based on what we've talked about so far, there's no reason not to give full credit for this answer as well, right? Okay, all right. So anyway, we'll stop the video at this point right here, and we'll finish chapter 6 with one more video.